Thank you very much. I'd like to actually start off by why we're doing this, the motivation behind all of this. That stems pretty much from the classical world. Putting computation at the hands of a large scale of computational science community of users was the motivation in setting up the classical HPC centers. And I'll use HPC as a loose term. It could be publicly funded, national level, regional, institutional clusters, or it could be the commercial cloud services that are offered by the industry. I'll use HPC interchangeably there. It's just, we see cloud is a mechanism through which to manage the resources and provision them for the end users. That's the modality of it. So from that perspective, quantum computation, we acknowledge that the readiness of the engineering of the devices themselves are pretty much low TRL, so think anywhere between 2 to 5, 6 at best. And thanks for bringing up the use cases perspective as well, because all of this is towards practical, usable computing at the end of the day that benefits science or society or environment. So the starting point for us is to leverage the experience that the HPC community has had in scaling up the usability of the classical computational systems at scale and putting and building with the vendors or the technology developers on one side, working with them on modularizing the entire stack so that it's interoperable. It allows for composing different modalities of computation and data systems in the classical world, building the software stack, and then working with the user community in understanding how to manage these tools, hardware infrastructure and software infrastructure, to do useful science. So it's leveraging all of those technical elements as well as the practices elements of having built this HPC community. And we want to help the quantum computational community to leverage this experience and not have to go through the painful experience of going, of doing this all of this again. So that's the rationale behind this. So we are not looking at operational readiness of the technology itself, the quantum computational technology. We are looking at the operational readiness of the accessibility of the experimental devices. So in that respect, I wouldn't go through each point. We have already been highlighted about what could quantum computing, when it's error corrected, when it's scalable, when it's reliable, bring to addressing better computations for parts of problems. So that's quantum accelerating or optimizing HPC. HPC currently has a lot more potential to offer quantum computation development as well. So that's scalable software emulators, for example. It's about the controllability of the devices, and it's also about how can we use HPC for modeling the behavior of quantum mechanics. And we are working with enterprises that are using, in a tight loop, the engineering of quantum devices and the engineering of the algorithms on the quantum devices on HPC platforms. So there is a tight interfacing between solving something on HPC and then feeding it into the quantum computing in real time. So these are the motivations from synergizing HPC and quantum. Now, this is happening at a kind of very siloed level. This is not everything. I would point you to the and growing part, because this slide, we did that in the context of IEEE Quantum Initiative 2 years ago, but this has exploded since then. Since then. This is just to say that the interfacing of HPC and quantum, whether on-site or remotely, has been happening all over the world and predominantly driven, for the most part, by the HPC centers. Given our geographical location, I'd probably draw our attention to what Yasser introduced us. Within the quantum flagship and the EuroHPC Joint Undertaking, there has been a movement towards bringing the technologies, devices that are being developed into the HPC centers by the JU, and it's been informally called the EuroQCS as like kind of the sister activity of the EuroQCI. And also there are the kind of Leibniz Supercomputing Center in Munich, Quantum Valley. There are regional activities as well. So there are pockets of activities happening all over the place. Each of us have been developing, so I represent the Irish National Supercomputing Center, but we are working together with almost all of the HPC centers across Europe, and also a few in the US as well. So we have been working on problems, the same problems of how do we bring these devices into the data center, how do we interface the software stack at different levels, how do we find practical use cases that would drive the co-design, because we need the applications to tell us as to how the interfaces should work, what latency models are we reasonably looking at, etc. So it's a huge co-design exercise, but we've been pursuing this for the last 3.5, 4 years, minus the last 6 months, almost blindsided by what each of us is doing. So that was the motivation behind what I'm going to talk about in a couple of minutes. But before the thing, when we talk about bringing quantum computing into HPC, again, we'll have to be conscious of different modes in which we interface them. They can be located on-prem, and even there are different levels of integration tied to loser integration. There are already demonstrations of federated integration in remote sites. So it's important to understand that all of this has an implication. All of these decisions have an implication on how the software works and what latency models are employed, what the programming models look like, what asynchronous or synchronous computation is possible at an application level, and what kind of applications then these integration efforts are going to support. There are a few schools of thoughts there, and the challenges that we face pretty much are, as I said, the quantum computational community has been kind of working almost in a silo and developing a quick solution through predominantly Python-driven software stack to bring it to the scientists' hands. That's good because it opens it up very quickly, but we'll have to also have a parallel effort in synergizing the stack going forward so that we don't have two communities of software stack which we have to re-engineer a couple of years later. And there's a huge interdisciplinary knowledge there. At least we have the classical software engineers, we have the classical HPC system operators, we have the quantum physicists and quantum engineers, and then we have the application use cases, which are domain specialists, which are again algorithmists, which are software engineers, and we don't speak the same language. You put us into a room, we'll come out more confused than we went in. So that's the experience we are facing on a day-to-day basis. I myself have a computer science and engineering background, but on a day-to-day basis, I get battered by physicists that I work with within and outside, and domain specialists. And on the other side, the technical side, what is the problems of integrating or interfacing, I would rather say, these two classical and quantum systems entail? It's at an infrastructure level of deploying and hosting the devices in a world which is noisy, which has a lot of vibrations, which the quantum devices don't like. Someone mentioned that they are shy, they are very angry as well. You poke them, they'll just go berserk. And then there is the systems side, the systems meaning all of the practices and software in the system software stack. So how do you provision access? How do you manage the resources? How do you quantify the size of a problem? We request core hours or node hours in the classical world. How do you estimate the size of a problem in a quantum world? That's not known. There are multiple models there, but how does one, when multiple users want to access the same device through a virtual queue, how does the device operator and the service provider quantify and allocate resources and manage that? What is the scheduling mechanism going to look like? What is debugging entail? How does one monitor these devices and so on? So, and then at the system software level, how do you synergize the programming model, the programming languages, the libraries between the classical and quantum world, and then the applications and the workflows, as I mentioned. And then, as I mentioned, the skills and workforce development, we are talking about interdisciplinary skills and a new breed of people skills being actually built. So there's an equal demand of not just the people that are being trained, but also the trainers who have to be built. Because typically when we deliver a quantum computational course, it's on page 2, you run into mathematics and physics. And that is consumable by the scientific community, but when you're talking about the domain users or the classical world people, it's a different way in which the training have to be conducted. So we typically end up having a cohort of quantum mechanics, quantum information people, computer scientists, software engineers, and use case domain experts co-building the material and delivering it together. So you can't have one lecturer deliver it end to end. And then how do we take this as a HPC-driven community in a phased fashion, because the devices are not mature yet, so you can't build for the next 15 years. So how do you phase this over time with the device vendors and the user community? So long story short, all of this conversation a couple of years ago brought a few of us as HPC centers together to say that, okay, let's actually have a meta program where we can at least start by sharing what we are doing with each other and build towards a knowledge base of this works, this doesn't work, let alone best practices and standards. We don't think it's the time to standardize, at least for this problem yet, because we don't have a stable way of implementing things. So it's at least sharing in a community environment in a systematic and structured way, best practices, our experiences, what is available now, what needs to be developed, and that's hosted within the IEEE Quantum initiative as a working group, the Quantum-HPC Working Group. But more importantly, it's not just HPC centers. We have day-to-day conversations with the quantum computational technology developers, including the hardware and software. We have our HPC people in terms of system architects, the vendors of HPC devices as well. We have the software developers, the system software developers, the programming model, the people from MPI, for example, as well, to learn from their experiences. And also the application developers and the use case owners, because we want to have a co-design. So those are pretty much the 5 pillars, so to speak, of the working group. I probably wouldn't go into too much of the details, depending on time. 4 minutes? Yeah, because, so maybe I'll just quickly run through these. The infrastructure management, as I said, is about how do you physically host a device within a HPC environment. What does it take in terms of installations? What does it take in terms of having a rack-compatible control module for your quantum device that fits the 19-inch specifications? How do you bring a device packed so that you can maybe have drop cables that plug into the power supply or the cooling system, etc.? What does it take in terms of operating procedures, in terms of you do calibration, you do benchmarking, maintenance, you just can't walk into a data center. So how does the quantum device provider manage all of that with the HPC operator? And then when it comes to system provision, as I said, we're talking about leveraging the operational tools and practices in a HPC center. So it's about authorization, authentication infrastructure. It's about resource allocation software. It's about policies of when someone requires allocation of a GPU accelerated node with a quantum node. There is a workflow that's happening, so you want to provision the device at runtime as to avoid any major break of the workflow itself. So how do you have a scheduler, a multi-level scheduler, which one, for example, in the lower level works as a virtual queue into a quantum device, but then a second level scheduler at the top is the cluster level scheduler, where you can access all of the resources as a unified set of heterogeneous compute units. So it's about developing all of those, and then it's about also looking at compilers. So quantum computers don't have ISA equivalency yet. We don't even know how they're going to look like going forward across multiple modalities, multiple vendors. So how can we build that level of abstraction and have ISAs feeding into the intermediate representations that we are so easily using in the classical world to build compilers, optimize them, and so on. So how do you build towards all of synergizing all of that? And then the software programming, again, programming languages, non-Python based would be good as well to widen the user community. And then looking at practical use cases as well. So not just classical hybrid use cases, but are there genuine use cases where the classical component would need a HPC node, even if it's a single node, even if it's a server level CPU or a GPU? Is there a valid use case where it really needs that level of acceleration? So we're still yet to find that. There are some candidates, but that is a big part of what we're looking at. And skills development as well. As I said, we're talking about people with the quantum mechanical and information science background. We're talking about people that can do good software development, people that can implement computational models, and people that can communicate the domain applications and algorithmics and workflows to these people to build the solutions or co-develop the solutions. And long story short, the middle part, it's not the ideal situation. Now we have a part of the classical world where things are hardware specific in infrastructure and in software, and then there's a kind of transition into a bit of agnostic pool of software resources. And then we go higher up, then it gets domain-specific languages, application libraries, and so on. So it's a spectrum, so to say, and not demarcated lines. But it's relatively better balanced in the classical world. You can almost have the same kernel, have different compiled versions to run on different architectures. But then in the classical world, you almost have a siloed vertical scenario now, the vertical being for different modalities, whether it's photonics, neutral atoms, superconducting, etc. And it's also siloed across vendors. So it's about, can we tilt the agnosticity from hardware to the middleware to the applications to kind of an equivalent tilt that we have in the classical world? Can we bring or leverage the quantum world towards the HPC side of things. And that's the conversations that's happening. So across LRZ, Munich, Los Alamos, Oak Ridge, and iCheck, we're just bringing the community together. We're not doing all of it, but if you wanted to know more, please feel free to reach out to this working group. And the way we are working is we are at ISC Quantum Week SC on an annual basis, but we're also looking at bespoke events where we just lock ourselves up for 4 or 5 days together and work on this together in practices, white papers, etc. So just feel free to reach out and happy to engage.
Thank you, Venkatesh.